Hi folks, just getting started. Take me another few minutes to get everything squared away. Whoops, don't want that to peak on the mic. Turn it a little bit down. Get my slides up, get my tabs open. What tabs do we need? I think we need our resources page. That's always a good tab. Probably remember what I'm talking about today. Something to do with computer organization and program execution. I think it's time to start. Go all the way back to the start of our lecture. I'm just going to start my recording, but it'll take me a second to get my remote control up here. Good morning, folks. How are you going all the way out there in computer land? Just getting myself sorted out to start this lecture, opening Microsoft Teams, looking at my chat. Make sure everyone knows we're on. I probably haven't started the video yet down on Microsoft Stream. Lecturing in a minute. I'm going to start my event. Apparently I've got streaming coming in. There I am. I must be live. Microsoft Stream started. My recording has started. I think Stream has started. It's always a bit of a mystery about how Microsoft Stream works. It's definitely the weirdest of the streaming systems. Getting a few thumbs ups from my folks on the forum on Teams. What am I talking about? Thanks, folks. Always great to have people watching me live. I'll take another minute just to let people let people wake up and get ready to go. I've got some viewers on YouTube, and there's a few faithful Twitchers out there. Thanks anybody who likes to watch me on Twitch. Twitch has like this gamified thing, like you can be an affiliate or a partner or a special sausage in some other respect. And the more people watch me on Twitch, the more I feel like I'm playing some kind of cool game where I'm pretending to be a video game streamer instead of being a computer science lecturer. So I should get the thing where you have the little emoji on Twitch or whatever they're called coming across your screen, or someone can press a button and confetti falls down, or there's a video of Barjo coming and doing something. Hole breached, goal reached. So ALU operations is the topic for today. It's been an interesting week, I think, for many folks in the lab so far. You've had chances to experiment with how instructions work on your microbit and try out a few little experiments, just like I was doing in a lecture on Monday, except by going even further. These for those of you who have been to your lab already. I know there's many labs today and on Friday, but for those of you who have done it, you have done this already, and those who will do it, you will get the chance, but you make your own encoding, you make your own instruction, you kind of jam it into the code without letting the assembler make it. So I guess the point of that exercise is to learn or have the experience of creating an instruction by hand, doing what the assembler does by hand, taking a line of assembly which we would like to happen, turning it into a machine language encoding, turning it into hex, putting it into our memory in the right order, and seeing that the CPU is like, cool, I'll run that line of code. As long as the instructions come in the right way, the CPU is cool with it. It doesn't care. It doesn't know whether it's come from an assembler or a compiler or it's something that you've just put in there by yourself. I saw someone had a shocked emoji on the Teams just then, and I would like to say, it is a tricky exercise. It's tricky, and you feel like there's sometimes you're doing something with a computer. This is the feeling I get, where you feel like you understand one level, and then you push it a level out, and then you push it a level out, and then you're sort of reaching to try to do something that you just understand, and if you can just hold all the ideas in your head, maybe you'll get it to work in that moment. That's one of those exercises where it's just a little bit tricky to keep track of it conceptually. I'm so pleased you enjoyed it. I can see people really getting into that exercise. So we're going to go a bit deeper on instructions today, looking a bit further in some more details about what can happen after an instruction runs. So I'm going to skip, I think, into the middle, where we had part two. We've already talked quite a bit about immediate versus register instructions. So you know now that there are some instructions, for instance, adds R2, R0, R1, which use 3 registers as the inputs. So take numbers from 2 registers, add them together, deposit it in a 3rd register. You know that there are other instructions that where you can put a number right into the instruction. For instance, the mov instruction, you can say mov R01, which will put a 1 in R0. And I know that there were some instances where people were starting to wonder, well, how do these immediate values actually work? And I think we pointed out that in the movs instruction, like if you look in the instruction reference, the maximum number of bits you get for your immediate value is 12. And that maybe seems like maybe a lot, but 12 bits is not that big of a number. What is it? 44,096? Is that the maximum represented number with 12 bits? Someone will tell me in the chat I'll look on this computer. 2 to the power of 12. Yeah, 4096. So can you really only represent numbers between 0 and 4096 with immediate values? Interesting. I'll just leave that one with you because it's a tricky concept, but that's how these work. The ARM immediate values have this limited number of bits. So the question is whether that's what's going on. If maybe you've tried some things. Some people have tried some things on Piazza and found some big numbers, bigger than 4096, seem to work, and some don't work, and we're not sure why yet. So just have a think about it. We'll get to that a discussion about what might be happening a little bit later. Okay, back to our little example. 2 versions of the add instruction. This one had the immediate value. There was one in 3 bits here dedicated to the register where we're going to output that value. I'll get my little pad back. Green, I really want green. That's the register output, and here's the 12 bits or only 1, 2, 3, 4, 5, 6, 7, 8 bits for input in that case. And there's our opcode. Then here's one for add with registers. We've got 3 3-bit register areas and 1, 2, 3, 4, 5, 6, 7 bits for the opcode. So they're, to some extent, they just end up as different instructions, right? They've got a different opcode, they have different inputs, but they have the same operation going on. So there can be, when you look in the manual, the reference manual, you might start to have seen that you get maybe like the add instruction has like 5 pages where there's different, maybe 5 is an overstatement, but there's a couple of pages of different encodings for the same operation in your microbit. Okay, we talked about this before, but I guess if someone wants to jump in the chat, tell me, why do you think we need both immediate values and register versions of these instructions? Why do we need multiple versions of instructions at all? Why do you think that would be a good idea? Oh yes, someone's in the chat who was trying to find the right encoding. They were checking my answers last night with Julian, I think, on the forum. That was really good work. I'm loving some of the questions we get on the Piazza now. Some really, really smart questions. People really being curious about it. Why do you think we might need different encodings for instructions? I'm going to keep talking. We might come back if people put some thoughts in the chat. So the instructions are the language of the CPU. You might program in a programming language like Python or Java, but the CPU only understands one language, that is machine instructions, in those encodings. And the ARM v7 reference manual gives us a list of all of the things that the CPU understands. It doesn't understand other stuff because it's not wired that way. It literally is only wired to accept those operations. Yeah, another idea about why do we need different encodings for instructions? Maybe some can be more space efficient. I think I talked last week about how ARM v7m is designed to be a space efficient language or instruction set. And if you can change as many instructions as possible to the narrow encodings, you save a lot of memory. Someone else says perhaps we have to deal with times where we need to put new data in and sometimes we need to use stored data. Exactly. In some sense, the MOV instruction is great because you can just get a value in there right now, and you can, if you're using the immediate values, for something like add, you don't need that immediate one, but if you didn't have it, you'd have to use a MOV to get the value initially. So it would take more cycles, more instructions to do the same result. So there you can save time efficiency, save time complexity in your program by using immediate values within your instructions. So the CPU understands these instructions. The CPU does what it's told. You give it an instruction, it does it. But how does it know what to do next? And that's what we're going to talk about now. I guess in some sense, you have an intuitive view about how a computer works out what to do next. Obviously, it just goes to the next line of code. But I think we're going to go now and just talk about how it knows what the next line of code is and what the process is. So the process for a CPU to know what it to do is its execution cycle. So how does it actually go to the next line of code, go to the next line of code, go to the next line of code, and do what it needs to do? And it's often called a fetch, decode, execute cycle. Those are the three kind of primary steps. And in fact, on the Cortex M4 in the microbit, those are exactly the three steps that our CPU has. So just thinking about this, the first step, to see what I mean, the first step is that the CPU gets the code out of memory. It's stored in program memory. Then it works out what to do with it. So it has to decode the op code, make sure the registers are all connected to be the inputs, make sure the output for where the instruction is going to go is connected. Do all of that preparatory work and then actually execute the instruction, get the two numbers out of registers, add them together, and put the output in where it is going. 3 steps in that execute cycle. So just to think about the registers here, we talked about how we had 13 registers that are just called R something, R0 up to R12. And then we've got 3 extra registers that have special names, SP, LR, and PC. That's these ones. And then we've got this extra special register, XPSR, program status register. We're going to talk about this one today. That's our special, something special to know about, PC. PC register, it's called PC. Its name is the program counter. The program counter. So when you've got your code, you know that lines of code are lined up, top to bottom, and your computer runs one, it runs the next one, runs the next one, runs the next one. When you encode use an assembler on your assembly instructions, turn it into a machine instruction program, the same thing happens. All of your code is lined up in memory. Boop, 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 boop. And the computer runs this one, it runs this one, it runs this one, runs this one, runs this one. And the program counter is like the bookmark, which is telling us where we're up to. I'll prove it to you. I'll just run this program. There's program counter, OX200, nice and low. It's nice and low on the microbit. On the hardware we used last year, the program counter would always start at a very high number, which was just a bit confusing. So it starts at OX200 in our OX200. It's not 200, is it? And when I move one instruction down, oh, now it's OX202, OX204, OX206, OX208, OXA, 20A, OX20E, OX210, 210. And then we go back. That's interesting. So it's like this bookmark, keeping track of where our program is up to. The PC records the memory location of where the next instruction is to be used, actually, not the current instruction. By the time we're reading the current instruction, the PC is already pointing at the next one to fetch. If you input Someone said that they noticed the reference manual gives a special behavior if you input 1111 as a register in various instructions. I'm not quite sure what you mean by that, so we might come back to that one. So, as I said before, when we are running a program, when I click down on the debugger, the microbit fetches the next instruction based on PC. It decodes the instruction to work out which operation it is using the opcode, and then it executes that instruction. The bits that were supposed to go where they go where they're supposed to be. And then we go back to step one and repeat this process over and over again. So it's called a cycle, the fetch, decode, execute cycle. That's not such a hard thing to understand, is it? I guess one interesting point is that the PC doesn't always increment. It's not always going up through time. Like when I ran my program, it goes up, 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 up. And then when I have now got this line of code, B main, you can see PC is 212 there. When I hit run on this line, it's now back to OX200. So this program has been lined up in memory, and the bookmark can go down, 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 down. But if I run that B main line, that takes my program counter back to the top, the start of that little program. Someone's asked another great question. How does the computer know whether to fetch a 32-bit or a 16-bit instruction? We talked a little bit about that last week, and there was actually a canonical answer on Piazza that Julian figured out for me, but it's based on the opcode. So I'm just going to view disassembly of main. Oh, what happened? The opcode, which is going to be F5 or 18 here, part of those bytes, there's particular patterns that you know, if you see that pattern, you know that it's supposed to be 32 bits. And if the microbit CPU gets that packet, gets that opcode in the first half word, then it knows, oh, this is not a 16-bit instruction, it's a 32-bit instruction, and that means I need to load another 16 bits in order to complete the instruction. So there's a list, I've forgotten what it was, a list of particular encodings. It's not something easy like it just starts with a 1. It's a bit more complicated pattern on the first 5 bits of the instruction. Status flags. This is really important. What's with the S in adds? What's with the S in adds? And I told you before that the S in adds stands for set flags. But what are these flags? Do I mean a flag we fly for our country or something? No, it's something else, isn't it? So I guess you might have wondered when we were looking at the ripple adder last week where the carryout goes. So at the end of the ripple adder, you'd have added some numbers. You know, we had some 3 bits coming in. I'm just going to make a very boring diagram of ripple adder. We'll just do a 1-bit adder. And that was the carry in. And coming out here is the carry out. Where does the carry out go? And the answer is that it goes into your status register, the program status register, as a flag. So it's sometimes called a bit or a flag. Okay, now we can see the status register here. XPSR, program status register. So if I open that up, you can see I've got a bunch of flags here: negative flag, 0 flag, carry flag, overflow flag, saturation flag, GE, I don't even know what that is, interrupt number, that will be important later, ICIIT, IT, thumb state. So these ones are important, but you don't need to know about them right now. We're going to talk about these ones today, the first 4 or 5. So if you do an add, and it turns out that you've got to carry the 1, that 1 goes into that flag, the carry or borrow flag. I'm pointing at my screen, but I should be pointing up here, that flag. So this program status register, it's always there, and it keeps track of different bits of state associated with your current computation. State, so some important information that we need to know in between instructions. It's stored, stateful. And the top of the carry flag, the 4 highest bits, are these really important ones. -0 carry overflow. They're important because they relate to the basic arithmetic operations that we've been talking about so far last week and earlier this week. Adding, subtracting, and just adding and subtracting. I suppose they also relate to the logical operations in some sense, but it's a bit of more of a stretch to see how it goes. In VS Codium, I showed you how that works. There's those XPSR flags, and S stands for set flag. So on any instruction where it's relevant, if you put an S on the end, it means that it will set the flags. And if you don't put an S on the ends, it won't set the flags. So whether an instruction has an S or not is often specified by a bit in the encoding, in some encodings. Some encodings are just either way. They don't need the S, the bit. And the important thing is that you don't have to. So I guess so far we've always done adds in these lectures anyway. Mobs, adds, NOP. But it's not required to do that. We don't have to put S in there. In fact, it's usually better if you're not setting the flags. If you know you don't need to, don't set them. And the reason for that is that if you don't want to accidentally overwrite them. If you've got some information in the flags you need to keep, you might like to keep it there for a few instructions and then use it. So, a little recap, and sorry for the contrast on this slide. Remember that we had our normal natural binary numbers. They just count up to the power of n minus 1, where n is the number of bits we've got to play with. And remember that if you go off the end, if you just keep adding 1, and you get to f, and you add 1, it will go all the way around back to 0. Someone's asked me what's the benefit of setting the flag in the adds example. There's no benefit for these examples right now. It was only there just to introduce the idea of S being an important thing that we have to do. So if you add 1 when you're at this end, plus 1, you fall off the end and you come all the way around, and then your adder would set the carry flag. The carry the 1 is kept. So if you have a number A, there's A, and if you have a number B, and you add A plus B, that's not going to fit. It's going to come out somewhere like there. That's A plus B. So we end up, the result of that addition ends up being A plus B is in this part of the number line, and the carry flag is set. That equals 1. So that's the output of the carry flag. The carry flag in that status register is defined to just equal whether there was a carry out or not in adding 2 numbers. That's its definition with the adds operation. 2's complement binary numbers. So when we are, I don't know why there's 2's complement. 2 complements there. I never noticed that before. When we're in 2's complement world, which is just, it's the same binary numbers, but it's just our perspective has changed, we can get an overflow on both sides, can't we? We kind of wrap around. So if we had A and B as positive numbers, we add those together, we will end up somewhere in the negative area. And if we had C and D, which are negative numbers, and we add those together, we should get, we add two Ds together, we still get a negative number. If we add two Cs together, we go this way around. We're always going the same direction. Our adder goes the same direction, but we end up with a number over here. So it's essentially we've overflowed. So I guess there's two different words here. One is carry and one is overflow. So carry means we've added two numbers and we need more bits. So there's been a carry out in the adder. And overflow is a specific concept. This is what I'm going to talk to you about right now. In this concept of overflow, it's a term which is often overused. We could use overflow in this example, that word, to say, describe what's happening when your number goes across the other end of the natural number line. But I'm going to define a version of overflow which is only applying to signed numbers. And the version of overflow is this. Overflow is when we've got two inputs, positive, and output negative. Oops. Hope you understand this plus VE and negative VE, positive and negative little shorthand notation. I don't know where I learned that. Maybe some weird thing from high school. That's overflow. And the other condition for overflow is two inputs negative, output positive. So in either case our answer is wrong. We're going to be in big trouble if we do this. If I've got A and B and I add them together in signed world and I end up with what I would consider a negative number, A and B are both positive. There's no way that answer can be a negative number. So I know that something's gone wrong there. I need to deal with it. If I've got C, a negative number, and I add it to itself, minus C plus minus C, that's going to be an even more negative number. It should be minus 2C. So if the answer there ends up being some kind of positive number, I know my answer is wrong. So that's what overflow means in signed arithmetic. These are both overflow. So you can see now that we're going to have to be a little bit careful about our interpretation of these numbers in order to understand what these words mean, carry and overflow. Oh, someone sent a message I just don't understand. Nuclear Gandhi. Cool. That's up there with POG as something I don't get. It might make more sense in a minute. One of the issues with these numbers is that we're always going in the same direction around the number circle. Because you remember our numbers were a circle going from 0, 0, 0, 0 to F, 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 F. Oops. And all of our additions happen in that direction. So we've got these different different ways of trying to make sure that we're not going to make a mistake when we're doing our addition, no matter whether we're considering signed numbers or unsigned numbers. The 2's complement circle. Ah, yes. It's a deep meme, someone is telling me. There was an old bug in civilization where the character Gandhi could have a aggression that overflows and just destroys every other civilization. So we're always going this way around the circle. If we had -3 and -3 added together, it's the same answer as 13 and 13 added together. But we've got a slightly different kind of issue, because 13 plus 13, what's that going to be? 26. Subtract 16, it's going to be 10. That's going to end up here. Oh, -3 and -3 is going to be 6, so that's not going to work. So -3 and -3 get to -6. Well, that will work. 13 and 13, we would end up with 10. So that's having a carry out situation. But if I add 10 and 10, what will we end up with? 4. Oops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll end up with 4, that's right. So that will be a carry-out situation. -6 and -6 will also equal 4. But in some sense, it was easy to recover from the first one if we're in unsigned land, because we can add 16. But it's a bit more confusing when our adding two negative numbers ends up with a positive number that doesn't seem to have anything to do with it. So we need to be careful of that. That's an overflow issue, where we've overflowed the range of the negative numbers, but it hasn't gone this way around the circle. It's gone the other way around. Okay, maybe I've just confused everybody. We'll go to the easier flag, the negative flag. This one's this one's not very hard to explain. If we do some addition or any operation on the ALU that has an S on it, and if the answer, when interpreted as a 2's complement signed integer, is negative, the negative status flag will be set. And I want you to tell me, how can the CPU tell if the 2's complement interpretation of a number is negative? That is a question for you. How does the CPU know? Whoops. That's right. Someone's asked me a question about my awkward explanation on the previous slide. I think I just want to delete that explanation. It was terrible. I'm just going to move on, and I'll explain it again more clearly later. A bunch of answers coming in. How does the CPU know an answer is negative? The first bit is a 1 of the output. So if it's OB 1 0 0 0 0 0, whatever, the CPU always knows that if this number was interpreted as 2's complement, it would be negative. So that's going to mean it's negative if 2's complement. Now, like the way that the CPU calculates the negative status flag, it's literally just copying that first bit from the output register. So if the first bit is 1, that means the flag is set. It's the same. The CPU has no idea whether it's 2's complement or not. It doesn't know what you intend. It just copies that bit across in case, right? And negative is only relevant if you're programming something and you're interested in 2's complement integers. If you're programming something with unsigned integers, then the negative flag, I guess, could be interpreted as the highest bit is set, right? It doesn't have any more specific interpretation. Let's try one to make it work. Ooh, this one will be good. Subtracting two numbers. We haven't done a sub. Mos 5, Mos 6. I'll delete my comments so that they're not wrong. Get rid of that. Subs R2. Okay. Sub S, subtract. We got a 5 in R0, we got a 6 in R1. Negative flag is 0. Shake it all about. Negative flag is 1. And what's the answer? FFFF, which is binary all ones. And in 2's complement, that is -1. Cool. The negative flag is 1. Okay, good example. That's great. We'll move on. The negative flag is easy. If there's questions about that later. I guess when we're combining these things, it's more complicated. But oh, we already worked it out. It's the same. That was just the same as this. I don't know why there'd be a talk slide about that. So what about the 0 flag? This status flag is set when the result of an ALU operation is 0. What does the CPU do to work out whether the result is 0? Someone tell me in the chat. No answers yet. How can I tell if I've got a number? Suppose I've got a 4-bit number. B0, B1, B2, B3, and I want to work out, is this number 0 or not? And I've only got logic gates to do it. Ooh, good question from someone. Someone in the chat saying, just sees if all the digits are 0, but how? I'm a CPU, I only have logic gates. I don't have eyes, I can't see things. I have logic gates. Do AND them all together and use a gate. You know what, the problem with that is if I AND them all together, supposing this is 1, and that's 0, and that's 0, and that's 0, then the answer is going to be 0. So that's going to tell me that it's or all the bits together and not the answer. That sounds more sensible. We're going to use OR gates. B1 or B0 or B2 or B3. So now that answer will be 1. No matter if there's a 1 in any bit, that'll be the answer. And I want it to be, check if it's 0 or not, so I'm going to not gate all of the things together, and that will give me a 0. But if it was 0 or 0 or 0 or 0, and we put a not there, it will be a 1. Good work, team. You just designed the way to work out a 0 flag in a CPU. Great CPU design moment. OR them all together. Yeah. Okay, let's do one. It was a nice example. I'm going to get rid of the S on the mobs. Someone told me to do that. I'm going to add 5 and -5. Just to see what happens. I'm going to put a NOP in here so there's just some space. Not a nope, a NOP. Whoops. I'm going to nope my way out of that one. Okay. Okay, where's my mouse gone? 5 in the first one. FFFFFFFB. FFFFFFFB in the second register. That's -5. If you hover your mouse over it, you can see decimal is a really high number. Oh, it's not going to give me a 2's complement representation. Bummer. Okay, now we're going to add those things together. Boop, we got 0 here, and the 0 flag is 1. Cool. It works. And it's just for someone's made a comment asking me to get rid of the S on the mobs. I can do that. It's not going to make that much difference because when you have an S, a flag setting for adds, it sets all the flags related to the arithmetic operation. So the flags, after I've run adds, there's no information in the flags here that's related to previous stuff, or the arithmetic flags anyway. It's overwritten them. Back to my slides. Carry. So this is set when the result of the ALU operation requires the carry out bit with that ripple adder. So we interpret this in the unsigned way. So if you're doing unsigned addition with these numbers and you end up needing a carry out, your carry flag is going to be set. And here's a good example. Mobs R2, OXFF00000, mobs R3, OXFF00000. That's going to overflow, not overflow, don't say that word unless you mean it, Charles. That's going to require a carry out when you do addition of those two numbers. I'm going to just choose another example. OXFFFFFFF and 1. I'm going to add those two things together. So we're right at the top of the range of unsigned numbers, FFFFFF and 1, and add them together. We get 0. The negative flag is not set. The 0 flag is set, and the carry flag has been set. Okay, but if I add 2, we will do the same operation. We'll find, I think, that the carry flag will be set, but the 0 flag will not be set. Ooh, negative flag not set, 0 flag not set, carry flag is set. Overflow. This is all about signed integer additions. So if the result of the ALU operation overflows the 2's complement signed integer in the interpretation I told you before, that means if you're adding 2 positive things together and you get a negative thing, or if you're adding 2 negative things and you get a positive thing, the overflow flag is set. Oh, well, now I'm confused. Smallest signed integer. Oh yeah, they're both positive. Yeah, I'm not confused. Excuse me, sorry, I said it. This one gets me. I have to really think about it. So we're going to have OX7FFFFFF. That's the biggest positive number in signed interpretations. And we're going to add 1 to that. So we've got a big positive number and another big positive number. If we were in unsigned world, this is fine. We can represent it. It's going to be 8000000, another unsigned number. But because we're in 2's complement, our answer is going to be a negative number and it will be wrong. That's that big positive number and 1, and we add them together, and our overflow flag is 1. Notice our carry flag is 0 because we're not in trouble in terms of unsigned arithmetic. It was a perfectly normal addition. We can completely handle this within 32 bits, but not in the, we can't deal with any addition of signed positive numbers. If we have 8, 0, 0, 0, 1, 2, 3, 4, and we subtract 1, oops, we'll also get the carry bit. We've got 2 negative numbers, and we end up with a positive number. There's our overflow bit. 7FFFFFF is positive, but these 2 input numbers were both negative, so things are not going to work, or it's subtracting a positive number, so adding two negative numbers together. If we overflow twice, will the flag get two things and then get 0? That's not how it works. The flags are just reset each time. If I run a subs operation, it is going to overwrite NZCO, NZCV. All four of those flags will be overwritten by the outcome of that operation, whether they're a 0 or 1. Okay. You might see like the symbol for the overflow flag is a V, not an O, and that's this V. V, and what was it? -0 carry overflow. -0 carry and overflow. So you just have to remember those letters there. So what can we do with these flags? Well, we're going to do a lot with them a little bit later in terms of choosing what path our program will take. Because the flags, to give you a slight spoiler, the flags give us all of our control flow information. So if you want to do if then else, you need flags. If you want to do loops, you need flags because they're stateful. They stick around and you can use the output of a certain operation to choose which path to go in your program. But we haven't covered that stuff yet. What we can do today is use a arithmetic operation, because we know about those. We're going to do add with carry. And this is an add, except it's putting the carry flag into the carry in, so that we can actually make use of it. Very interesting. So if I do it right now, I'll just do this example. 5, and that's 6, and I'm going to add with carry, what was it, 16 and 10 or something. I'll just look back on my slide. Probably it was relevant what those numbers were, 5 and 16. So far this is not going to do very much, because I think my carry flag is, my carry flag is 1 for some reason. I don't know why the carry flag is 1 there. Someone else was doing, in the previous code that runs on the microbit to get set up, it's left a 1 in the carry flag. And I'm not changing it. So now when I do this operation, 5 plus 16, I'm going to be including that carry flag in my calculation. So instead of OX15, it's going to be OX16. Oops, I've lost my mouse. OX16. Interesting. I can change the answer by putting a S on the MOVs here, which will clear the flags. Five. Oop. Or not. Oh, it doesn't change that flag. You have to look in the reference manual if you want to know the flags that any particular instruction actually changes. We need to know about that. Will be on our assembly cheat sheet. I'm almost out of time. Uh-oh. I gotta hurry it up. Moves and shifts. Yeah. MOV only changes the NZ flags. It can't change NZ, that should change the C flag. I don't know what it means in that case. Oops. Where are we getting to this? We can do addition with by treating two registers as different parts of a 64-bit register by using this ADC flag. So if we added to the lower part of two 64-bit numbers, we could do that with add R2 and R4, supposing those were, as written here, the lower parts of two 64-bit numbers. adding those together, if they end up with a carry, that's stored in the carry flag by this instruction. And then ADC uses the carry to add R3 and R5, the top halves of the 64-bit number. And then you would have the correct 64-bit result. Sometimes flags boggle me a bit, so it's okay if they're boggling you at this stage. It's the kind of thing that you need to get a little bit of experience in your labs to try it out, and you will do a lot of flag work over the next few weeks. More flags. There are lots of extra ones in the status register. We had a look at them, but these N, Z, C, V, they're the main ones. They're the ones that you need to know inside out how they work. I expect some confused questions on Piazza of people trying to work out how the flags work, thinking, hey, wait a minute, Charles said this in the lecture, but now I'm confused about why it's that way. That's great. Ask those questions. And for everyone else, if you don't ask a question, make sure you're checking the Piazza to see the questions other people are asking. Because when someone else is asking a question, often there's a great discussion about what the right answer is. Do we need to make sure all the flags are clear when you run our own instruction? Kinda, yeah. But you don't, it's not something you need to worry about too much because you typically use the flags having just run an instruction where the flags are set. So I was doing an ADC by itself, which no one would ever do in their right minds. There's no reason to do that. You use ADCS after you've just done an add with flags from the lower half of your number. So typically you would do some instruction, you know, XXXX, this one sets flags, and then Y, that uses flags. And you'll put these two instructions quite close in your code together. They might be just one after each other. So you don't typically need to worry too much about clearing flags in particular in order to get work done, because you will have done a flag setting operation and then you will use the outcome of those flags. And the knowledge about which flag setting operations do certain things will be part of what you're experiencing from trying them out in the labs, trying to get certain things to work. Yes, and if you're just coming from first year computing and you've done Haskell, you are living in a world of lovely pure functions with no states or side effects that stick around on your computer. But really how your CPU works is it does have a lot of states and side effects. And you could see that there when I was trying to do an example with ADC, but somehow in the startup code, the carry flag had been set. The startup code is this, whoops, in lib there's a bit startup.s. This is the code that runs before your program. So when you turn on your microbit, it runs this code in the reset handler. There's a lot of great comments here from the tutors who put this together. Sets up your memory and data. Someone says, when we won't set any flag, but has been on from a formal program, will it affect our results? Well, it would if you didn't set the flag, but you're never going to run a instruction which relies on flags unless you have just put one in that sets flags, because otherwise there'd be no point running that instruction. And if you run an instruction which relies on flags without having set it, you're not writing a good program. And it's the programmer's responsibility. I was going through that a lot in the lecture on Monday. It's sort of your responsibility as the programmer to make sure that you only look at the flags when you need to and you have set them just before, because some other program could have changed your state. But you're right, it's a complicated topic, or it's a complicated thing to have to handle, and you don't expect to have to handle it, but you do, because assembly programming is a bit messy like that. I mean, a typical example could be, supposing I did this, this is just for an example, I'm not going to actually run it. Okay, add together your lower half of 64-bit number, add together upper half of 64-bit number. So this is the example we just had on the slide. All right, well, you know, as an assembly programmer, I could go and call a function bl some random function. We haven't talked about functions yet, and we're not going to for two weeks, but just let it sink in your mind for a minute that when I run this code, bl some random function, the program counter is going to go somewhere else in my program. It's going to run a whole lot of assembly code that I don't know about. It might be somewhere else down below, it might be in a different file, who knows. And then when that function returns, I come back to this line, I have no assurance at all that the flags are the same as they were before. In fact, I have no assurance at all that R2, R0 and R1 are the same as they were before, and R3 is the same as it was before. This function could have overwritten all of those registers. So, like, you would never do this. Do you have ADC versions of the signed number additions? Huh. I don't really think so. I don't think it works like that. Have you looked in your thing? No, I don't think so. Is there a command that we can use at the beginning of our function to clear the flags first? Not an instruction by itself, I think, unless I'm wrong. One of the tutors will tell me if I'm wrong. You could probably think of some kind of add or something which will definitely clear flags. Look in the instruction, the V7, oh. This is one of these things that I can't remember. I feel like I knew the answer to that question before. Not the cheat sheet. Well, I'm never going to be able to find it by Googling. Good question for the Piazza. We're at the end of our lecture time, so I'm just going to try to run to my final slides. Oh yeah, okay. Just to show you, these are the instructions, the arithmetic instructions that we have sort of covered-ish so far. Add with carry, add with carry. I guess for the signed number additions, you can use the sub with carry, but it's probably works in a weird way. That would be for borrowing when you're going the other way. So I still don't think it's going to work for signed. It's for unsigned subtractions. Sub, other version of sub with carry with immediates. We've got the register versions of things. We have the immediate versions of things. And then there's another one, a weird one called Q sub, which is the saturated version of addition, of subtraction, and the saturated version of addition, which work in a slightly weird and different way, and it's not likely to be something you'll need to use. There's been a few good questions which I'll need to take on notice. I guess I just wanted to come back to this point of the immediate values in instructions. There's a blog post which is listed here. It's linked from various places in the lectures and one of the labs, where it talks about how these immediate values actually work. So this is a 32-bit ARM command. It's not an ARM v7m post in particular. It's for other ARM ISAs, but the the concept is similar because it's a specific thing about ARM processors that they have these 12-bit immediate value encodings. And the trick is, when you have the 12 bits, some of it is used for an actual number, and some of it is used for a rotation around the whole range of 32 bits. And that means that you can have all the numbers from 0 to 256 right here, and then you can have all of those numbers from 0 to 256 shifted into weird patterns all around. So they do a strange kind of ways to let you encode useful numbers within 12 bits that cover the whole 32-bit range. And you'll have more experience in how those immediates work a little bit later. But sometimes you might mov some immediate value in and it works, and you think, cool, that one's good, and you mov another one that doesn't work, and you think, oh, how annoying, I'm gonna have to get that in a different way. And in fact, there's a way in assembly, in the assembly programming, to do a mov which always works, and the assembler just puts in, it knows about the ARM encodings, and it puts in a mov or a load from memory automatically on your behalf, just to help you out to load in any immediate value. Last question, someone has said, is setting flags more expensive? No, it is not. It is not more expensive. It takes the same amount of time. Typically, for all of these instructions, it's just one cycle of the processor to execute the instruction. It's all that we're doing when we're saying setting flags is connecting those wires to the outputs or disconnecting them. And the output's still there, it's still happening. For no extra credit, someone designed for me, based on the information we gave in this lecture, we did the logic circuit for negative is easy, that's just like equal to bit 31. 0, we had the ORing them all up and then putting a knot around it. Carry equals carry out from the addition. What about overflow? How do you do overflow in logic gates? Someone tell me the answer to that question on the piazza. It is 10 past 11. I know there are folks in a lab right now. I'm happy that we got to the end of this lecture because it's a complicated topic. I'm sure someone's going to come up with a good question this afternoon. I'm going to have to think about that one. Daniel was in the chat really pinning me down on whether you could clear flags at the beginning of a function. I don't know because I've never done it, because I never had to do it. So maybe it's just me, or maybe there's no easy way to work this out. Okay, I will see you folks on Monday. And now I will go to my outro screen. See you later.